Atomic Physics, Lecture 3. Hydrogen-like atom and Schrödinger equation for it. Paragraph 1. Hydrogen-like atom. Since an atom is a system of a large number of parts, the wave equations that describe it turn out to be very complex and usually cannot be solved analytically. The exception is the simplest case of so-called hydrogen-like atoms. In this case, the equations describing the atom can be solved in an exact analytical form. A hydrogen-like atom is an atom consisting of a massive nucleus and only one electron. Hydrogen-like atoms, in addition to the hydrogen atom itself, include the following atoms. 1. Atoms of the lightest elements, such as helium, lithium, beryllium, and boron, ionized to a one-electron state. 2. Atoms of alkali metals in which one outer valence electron is in a highly excited state in an orbital with such high energy that the remaining particles of the atom look like a single point charge. Since the charge of the nucleus is screened by the charges of internal electrons, the nucleus plus internal electron system obviously has an effective charge equal to unity. Note that in order to achieve a hydrogen-like state, the excitation of alkali metal atoms must be so strong that atoms in this state do not exist under natural conditions. A highly excited state is created artificially, for example, by irradiating an atom with resonant laser light. To give an idea of how strongly an atom needs to be excited, we note that when the electron is excited, it ends up in an orbital so far from the nucleus that the size of the atom increases by about 1,000,000 times compared to the unexcited state. Note that the nuclear charge in a hydrogen-like atom, unlike the hydrogen atom, is not necessarily equal to unity. It can be greater than 1. The latter occurs for ionized light nuclei. So, helium has a nuclear charge of 2, lithium has a nuclear charge of 3, etc. Paragraph 2. Applicability of the solution for the hydrogen-like atom to other atoms. As you can see, hydrogen-like atoms are not widespread type of atom. Other than hydrogen itself, other hydrogen-like atoms do not exist in a natural state. However, the case of a hydrogen-like atom is of particular interest due to the fact that the exact solution obtained for a hydrogen-like atom can be used to approximate the description of many electron atoms, for which, as mentioned above, there are no exact solutions of their own. Such an approximate description is possible due to the fact that in multi-electron atoms, the interaction of electrons with each other is much weaker than their interaction with the nucleus. Therefore, to a first approximation, each electron can be considered as interacting with the nucleus independently of other electrons. Therefore, having found the orbital structure and energy levels for a hydrogen-like atom, one can use these parameters to describe multi-electron atoms at a first approximation. Paragraph 3. The task of describing a hydrogen-like atom. Let's consider a hydrogen-like atom, that is, one electron moving in the field of electric attraction of the nucleus. To describe a hydrogen-like atom means to determine in what states its electron can be. An electron in an atom can be in different states. In particular, it can be in different orbitals, have different energies, and different spin directions. That is, in each state, the electron occupies a certain orbital, has a certain energy and a certain spin direction. Therefore, it is necessary to find exactly what states the electron can be in. That is, find the spectrum of possible states of the electron. This means that we need to find which energy values, orbital parameters, and spin directions correspond to each other. According to quantum mechanics, each state of any quantum mechanical object is described by a specific wave function. This means that in order to find out what states an electron can be in, we need to find its wave functions. Wave functions are found by solving corresponding to the problem the wave equation. First, let's consider what wave functions are obtained as a result of solving the Schrödinger wave equation, that is, in the Schrödinger approximation. Then, we will consider the spin and relativistic correlations to the Schrödinger approximation resulting from solving the Dirac equation. Paragraph 4. Schrödinger equation for an electron in the field of a nucleus. When writing the Schrödinger equation for a hydrogen-like atom, the potential energy of the electron included in this equation is written in the form of the centrally symmetric potential of the Coulomb field of the nucleus. This potential energy depends on only one variable, the average distance of the electron from the nucleus. In Cartesian coordinates, the distance of an electron from the nucleus is expressed through the coordinates of the electron according to the Pythagorean theorem. Namely, the square of the distance from the nucleus is equal to the sum of the coordinates of the electron coordinates. In this case, the origin of coordinates is chosen at the point where the nucleus is located. An electron has 3 degrees of freedom, corresponding to its 3 coordinates in 3 different spatial directions. That is, its wave function is a function of 3 coordinates. This means that the Schrödinger equation is a set of 3 equations, one for each coordinate. However, in the case of a centrally symmetric field, it is not very convenient to work in Cartesian coordinates. Therefore, as in a similar problem in classical mechanics, for convenience we move from Cartesian coordinates to spherical ones, that is, to the radial coordinate and 2 angular coordinates. It is obvious that in such coordinates the wave function is a function of the following 3 variables, the radial coordinate and 2 angles. Paragraph 5. Schrödinger equation in spherical coordinates. In spherical coordinates, the Schrödinger equation splits into 2 independent equations. The first of these equations is the equation for the radial part of the wave function, that is, for the part that depends only on the distance from the nucleus. The second equation is the equation for the angular part of the wave function, that is, for the part that depends only on the angles. As a result of solving the first equation, the dependence of the wave function on the average distance of the electron from the nucleus is found. As a result of solving the second equation, the dependence of the wave function on the angular coordinates of the electron is found. Moreover, this last dependence can be expressed as a dependence on the angular momentum of the electron.